Welcome to our 11th exercise about energy storage. So we got a system which is quite equivalent to the one we used for calculating the photovoltaic power generator. So it consists of a refrigerator which runs permanently during the whole day, 24 hours, with a power of 50 watts. LED lights with a power of 4 watt each, 10 pieces. They run from 6 p.m. until midnight. A TV set of 150 watts, which runs from 8 p.m. to 11 p.m. Then we want to know which battery type is the cheapest. So we have one option which consists of an automotive battery of 12 volt and 100 ampere hours. It's usually a lorry battery, a quite big battery, which costs only 150 euro. The lifetime is relatively short. At 50% depth of discharge, it survives 1000 cycle. If you go cycle it deeper, for example 70%, it only has a lifetime of 500 cycles. Output voltage is 12 volt, but you have to consider, if you do the energy efficiency, that the charging voltage is 13.5 volt. The ampere hour efficiency of that battery is 90%. The second option is an industrial battery that we can customize by buying 2 volt blocks, which are available in the from 200 ampere hours until 1000 ampere hours. The price is specific at 200 euro per kilowatt hour. Lifetime is much longer. It lasts 3000 cycles at 50% depth of discharge and 2000 cycles at 70% depth of discharge. Output voltage is 2 volts, charging voltage is 2.4 volts, the same as before. The ampere hour efficiency is 90%. How much does 1 kilowatt hour in a storage cycle cost? In total, including the PV generation cost, the cost for PV electricity is 10 cents per kilowatt hour. Next part is now almost sector coupling. We use a thermal storage, consists of a PCM material, that means phase change material, for example ice, so you can freeze it, and by freezing it can contain a lot of cold, but so you don't need to supply any power for the refrigerator until all ice is molten. So you can generate ice during daytime, and the ice gets molten during nighttime, and the refrigerator stays permanently at 0 degrees. So during the day, the refrigerator and the PCM are directly operated by photovoltaic at this cost of 10 cents per kilowatt hour. The charging and discharging of PCM is not very efficient. Here we take efficiency of 60%. How much is the maximum price of the PCM equipment in order to be still competitive with the cheapest battery option? Lifetime of the PCM system is estimated to be 10,000 cycles. Usually the ice can last longer, but some other PCM materials often consist of paraffins, and they have a limited number of cycles. So let's start here with the first part, and we calculate the consumption here. Total consumption here 50 watts times 24 hours, then the LED lights 10 times 4 watts times 6 hours, and the TV set 150 watts times 3 hours. We have a total electricity consumption of 1890 watt hours per day. So we do a battery layout. So while we are on the topics, we choose an extra day and night of autonomy, so 2 days of autonomy in total. And for the costs, first we calculate for this automotive battery at 150 euro for a 100 ampere hour battery, which we can discharge by 50% only first. So the size necessary for 50% depth of discharge, so it's a load. Then we have to consider um, the ampere hour efficiency, and do not forget the voltage efficiency in order to get the energy efficiency, because we have to charge at a higher voltage than we get later, so there are additional losses and these have to be considered. And in total we have an efficiency of eta B times eta ampere hours, and so we choose this factor 1 divided by this total efficiency times the days of autonomy for the size of the battery, and divided by the depth of discharge, which is 50%, that means 0.5. So here we put in the numbers here, 1890 watt hours times 2 for the days of autonomy. Then we have the voltage efficiency, also divided by 12 volts divided by 13.5 volts. And then we have here the ampere hour efficiency, which is given at 0.9. And here we have the depth of discharge 50%, so it's a factor here of divided by a factor of 0.5. So in total, our battery size has to be 9.45 kilowatt hours. While one single battery of 12 volt, 100 ampere hours has 1.2 kilowatt hours, we have to choose 8, more exactly 7.88 batteries, but we don't get any percentage of a battery, we only get entire batteries, so we have to choose 8 batteries, and that means an invest of 8 times 150 euro, and that's 1,200 euro, and this will last for 1,000 cycles. So we have here the costs, this big K about the total costs for lifetime. So we have the number of cycles, then the load and so on, and the efficiency, and the specific cost for PV, 10 cents per kilowatt hour. So we have 1,000 cycles. Then the consumption here, 1.89 kilowatt hours. Then the efficiency, and then the cost for the PV cost. So in total we have 236.25 euros, and that is here we have to add up here. So this is for the cost of the battery, and this is the cost for the PV to be generated here, and then we have a 1.44 euro per daily cycle, or while we consume less, so it's only for the actual consumption 76 cents per kilowatt hour. Per kilowatt hour. The other one is per cycle. While a cycle is more than 1 kilowatt hour, so this is almost double. So this is almost 2 kilowatt hours, 1.89 kilowatt hours. So now we come to the calculation for 70% depth of discharge. So the same formula here is above, and we put in the numbers. So load is the consumption is still 1.89 kilowatt hours. The days of autonomy is still 2. The depth of discharge is now 70%. So we have here divide by a factor of 0.7. Then this is the same. The efficiency are still the same. So we have here ampere hours efficiency 0.9, and voltage efficiency consists of 12 volts divided by 13.5 volts. And in total, we need a smaller battery, which has 6.75 kilowatt hours. While one battery is the same as before, it's the same battery, 1.2 kilowatt hours, we need 6 batteries, exactly 5.62 batteries. And the invest is much less because we need less batteries, but it only lasts for 500 cycles. So the PV energy costs are here about the same doing this, but we only have 500 cycles. So we have 100 must be about it must be half of it. So we have here 118 0.125 euro during this 500 cycle of lifetime. These are our electricity costs for the PV. Plus the cost for the battery, these are 900 euros. In total, it costs 1018.125 euros. That means for a daily cycle, we spend 2.04 euros or 1.07 euros per kilowatt hour of consumption. So you see directly this is more expensive. So it doesn't make sense to increase the depth of discharge. Better stay at low depth of discharge here and yet 50%. The second options, now we buy the more expensive battery, the industrial batteries. Actually, we don't buy the battery, we buy single cells, which are available in several cells, and you put them together to the desired voltage, and they cost 200 euro per kilowatt hour. Lifetime is much longer, 3000 cycles at 50% depth of discharge, and 2000 cycles at 70% depth of discharge. Output voltage is 2 volts, so we have to buy 6 cells in order to get to 12 volts, and charging voltage is 2.4 volts, ampere hour efficiency 0.9. So the size necessary here, same formula as before. The load and the efficiencies and depth of discharge considered here, divided and the days of autonomy. So we have here, same as before, 9.45 kilowatt hours. So for 12 volts, 6 cells are necessary. The necessary capacity of the cell, there's a big C, the capacity, so this is the energy content of the battery divided by the voltage of the battery. So it's 9.45 kilowatt hours divided by 12 volt. So we have 787.5 ampere hours. So it's not really, we get any size, we just have to go for the closest here, or the close and bit upper, because we don't want to undersize it. So this is 800 ampere hour blocks are closest here, and we need 6 of them. So we are on the safe side, we have 9.6 kilowatt hours, and it is more than the necessary, and at costs of 200 euros per kilowatt hour, we have an invest of 1,920 euros, and it lasts for 3,000 cycles. So the costs for that are 3,000 times the size of the battery here, 1.89 kilowatt hour, and the size, the energy consumption, sorry, and this is the efficiency of the battery, and then we have doing this 3,000 cycle PV electricity costs are 708.75 euros. In total, battery costs plus PV electricity costs for 3,000 cycles are 2,628.75 euros, or 0.876 euro per daily cycles, and or 0.46 euro per kilowatt hour of consumption. So that's already cheaper than the automotive battery. Let's check the 70% depth of discharge, same procedure. So we but need our smaller size, because we have a depth of discharge of 70%, but it so the battery size is a bit smaller than that, and we still need 6 cells, because it just depends on the voltage, and the capacity of each cell of the battery is 562 ampere hours. So we need the 6 blocks we knew already before, but we now have a smaller capacity of 600 ampere hours each, and in total we have 7,200 watt hours. So that's more than our necessity, our requirement. So this works out, and the investments at 200 euro per kilowatt hour, 1,140 euro of investment, and lifetime is only 2,000 cycles, And here we see, if we put here doing 2000 cycle, electricity costs of PV are 472, plus the cost of the battery are 1912.50 for 2000 cycles. It means we have 95.6 cents per daily cycle, or 50.6 cent per kilowatt hour. You see, per kilowatt hour, so this is the cheapest option. Industrial battery operated at 50% depth of discharge. That's our solution. Let's come to the second part here. So the refrigerator can be equipped with a PCM material, for example, ice here, and so we don't have to consider battery during nighttime. We have to just, at least for the refrigerator, we have just to consider for lightning. We still need electricity, but we can choose a much smaller battery. So for comparison, the cheapest battery option we choose before, so this was here what we saw transparently before, 46.4 cent per kilowatt hour. And now we calculate the share of the consumption by the refrigerator, and during 24 hours it consumes 1.2 kilowatt hours, and we can power half of it directly during daytime, and nighttime there is no photovoltaics, so we have to cover it via battery or via the PCM material. The daily cost of the refrigerator via battery is, this is the consumption if we just power it by batteries, of 55.7 cents. This is the cost for the, so it's a bit more because it's more than 1 kilowatt hour. So the PV electricity costs, these are the costs for the PCM. So they just calculate the refrigerator with the PCM solution. Now this share, the other lights we calculate later. So this is the cost of PV, 10 cents per kilowatt hour. The consumption of the refrigerator during daytime, and during nighttime. And we have to consider the bad efficiency to create PCM material. So we have to create ice cubes with an efficiency of 60%. So we have to divide by 0.6 here. So this is our divided by half. So we need 600 watt hours per day and during daytime, and 600 watt hours during nighttime, divided by the conversion efficiency, and multiplied by the specific costs. We have costs of 16 cents per day, consisting of day and night. So we have now the cost for battery, which was the original solution. With powering the battery to nighttime, the rest doesn't change, so we just consider that part, and we just see here we only need 16 cents. So for that part, and so we can here take that off. So we have 50.5 55.7 cents per day per daily cycle, and 16 cents as we calculated before. So in total we have 39.7 cent on PCM we can spend on PCM, because that's the one that's the stuff we save, and we can spend it all on equipment. When it lasts 10,000 cycles, the total price of PCM may reach a maximum of 3,970 euro. It's really a lot. Usually, if you calculate it realistically, it would be some 10-20 euros or something like this. And not water costs nothing, but maybe you have to have an extra box or something like this. So you have an absolute benefit here, because you can spend such a large amount and it's still profitable. Yeah, I mentioned 20 euros for the cure, including casing. So you spend really, you save about 9,000 3,950 euros for that option. So that's really a good idea to use this PCM. Thank you very much.